What I'd really like to do tonight is tell you a story. And that story is one of space exploration. And it's also one of what our local neighborhood is like in our star system and all the space that's between our planet, the other planets, and the sun itself. I would like to give special thanks to Don Gurnett, the late Don Gurnett, Bill Kurth, and Craig Kletzing, all at the University of Iowa. They helped me tell this story, and all my mentors and mentees that I've had the privilege of working with throughout the years. So we're going to start with a map, because in every journey you should really start with a roadmap, okay? So we're going to envision our sun at the center of our solar system, and we're going to zoom way out to the edge of that solar system, and we're going to look at how that solar system is situated in the greater space around it. So this is a really nice animation that shows the solar wind that's emanating out of the sun all the time. That solar wind is comprised of charged particles and magnetic fields, and it's just always blowing out of that sun. But what happens when we get to the edge of where that sun's influence ends? Okay, this is what we call the heliopause, or the edge of our heliosphere. Helios meaning our sun. And outside of that heliopause, we have this immense, vast region of gas and dust that we call the interstellar medium. And that's just all the stuff that's between our star and all the other stars. But what we really want to understand is that local neighborhood that's enveloped inside of that heliosphere. So that's what I'm going to really focus on today, is talking about our heliosphere, our place in our local star system, and what that means and how we've been able to explore it. Okay, so this is what the roadmap of our journey tonight is going to look like. I'm going to start by introducing what space plasma is and talking a little bit about magnetic fields. I'm going to then go into our sun and its eruptions and the effects that those eruptions have on the planets in our solar system. We're also going to talk about space plasma near Earth. So there's things that you're probably familiar with, like the aurora, and then maybe some things you're not as familiar with, like the Van Allen radiation belts. And then we'll go on to talk about the Iowa legacy. I'm here sort of as a representative of the University of Iowa and all the space exploration that has been a part of that institution for so long. So I want to just touch on that a little bit. And then we're going to move out to a magnetically active planet, but a giant one, Jupiter, and just bring in how that is related to what we've been talking about. And then we're going to talk about our heliophysics observatory fleet as a whole. There's going to be a brief intermission, which you'll see what happens during that intermission. And then we're going to go on to the infamous Voyager mission. And then I'm going to end with some really cool sonification of space, where I'm going to play for you the sounds of some of the plasma waves that we observe in space. All right, so let's get started. We're going to start with space plasma, because this is something that's not that familiar to a lot of people. I've already said that solar wind there is going to consist of magnetic fields and charged particles that we call space plasma, and it's going to emanate throughout the solar system and just kind of fill all of what we sort of think of as empty space. And then this is going to create an ocean of plasma. So I like to think of this as just a vast ocean in which our planets and other objects are embedded. So they're not just hanging out there in empty space, they're really in this sea of plasma. When we have planets like Earth with strong magnetic fields, we can deflect a lot of that solar wind. Some of it makes it inside of our magnetic bubble, but a lot of it is diverted around the edges of that. And so I like to think of this as a rock that is sitting in a body of flowing water. Okay, so that's the solar wind that's coming over our magnetized planets and our unmagnetized planets and creating things like a shock wave in the front and a cavity behind it, right? Just as you would see in a fluid where you have a rock embedded in it. So just like an ocean, there are waves in space. Here's an example of observed plasma waves down here on the bottom left. Okay, this is just an oscillation of an electric field. We see these in electric fields, we see these in magnetic fields, and when they're in a space plasma, we can observe them as space plasma waves. This is an artist's conception of what some of those waves would look like along the magnetic field lines that emanate out of our planet. And just like in an ocean, There's also currents and channels that exist in this space plasma sea. And those currents and channels direct the motion of charged particles. And those are our magnetic field lines. Okay, so I like to think of those as our currents, which charged particles need to follow. And remember that all of our planets that are intrinsically magnetic, like Earth, like Jupiter, like Saturn, they have essentially a bar magnet, or we can approximate a bar magnet as sitting in the middle of that planet. And that's really what generates that magnetic field. So we all kind of have this picture of a bar magnet and the field that it creates. Well, our magnetized planets create that same magnetic field, but we have a little bit of a distortion. We have a little bit of a distortion because our solar wind is constantly blowing against that magnetic field. Okay, so if we move to the sun and we talk about the sun itself and how it looks under different conditions, we can identify what we call solar maximum and solar minimum. Solar maximum, you'll see, looks a lot more active. There's a lot more going on the surface. We can see sunspots and active regions kind of continuously across the face as it rotates. Whereas in solar minimum, things look pretty dim, pretty dark. And we just have a lot fewer of these active regions and sunspots. So these active regions are going to be the things that create our solar wind explosions or transients that can propagate through space and end up affecting our planets. And this cycle repeats itself about every 11 years. We are in the middle of an upward phase right now, and we're hoping that the solar maximum is going to be a good one. And it's projected to occur sometime around July of 2025. So we've got a couple more years while we're in this ramp up phase. And so we might even see some more solar wind events and some more aurora as well during that time. Okay, so this is going to be a video of a coronal mass ejection, or what we call a CME, from back in 2012. This is an enormous blob of material that can lift off the surface of the sun and go radiating out into interplanetary space. If Earth is in the pathway of that CME, we will know it. Okay, we see the effects of that. We have effects on our radio transmissions. We have effects sometimes on our satellites and our cell phone signals, our GPS signals. And we also see aurora. We see aurora, but we also see aurora at lower latitudes during one of these big events that creates a nice geomagnetic storm for us. So we really try to pay attention to these CMEs and track when they're headed towards Earth and when they're not headed towards Earth, so that we can better understand how they couple into Earth's magnetic field. As the solar eruptions propagate through the solar system, they actually weaken a little bit and they spread out and diffuse. You can kind of see this in the simulation here. They get a little broader and they get skinny, and they kind of, as they spiral outwards, they just get a little bit weaker. So a lot of our big impacts are going to happen on our inner planets. So everything in our inner solar system there. Once these solar wind transients get out to the orbits of Jupiter, Saturn, and beyond, they tend to be a lot weaker, and they don't have as much of a punch as they hit those planets. But we really get the nice big punch down at Earth because we're so close to the sun. And you can just see that pattern of how they extend and how they diffuse as they move outwards from the sun. So we have effects of these solar wind transients on Earth and on other magnetized planets. What I wanted to do here was compare how the solar wind affects Jupiter with how it affects Earth. So we're going to talk a little bit more about Jupiter in a few minutes, but Jupiter has a very, very strong magnetic field. You can see it's very large, even compared to the planet being larger itself. And when the solar wind hits when that solar wind transient hits Jupiter, it doesn't really distend and distort the magnetic field as much as it does with Earth. Okay, so if you watch the one with Earth, it really pulls that magnetic field behind it as it moves. And with Jupiter, it stays a lot more rigid. It doesn't have as much effect on it. So our planets in the inner solar system certainly feel that punch from the sun a lot more than our outer planets do. Okay, so this is the whole life cycle of from that solar wind transient over to Earth and the effects that it has on our magnetic field. You're going to see in a second that there'll be a CME that lifts off the sun, and it's going to hurtle towards interplanetary space towards Earth. It's going to affect the magnetic field on the front here, facing the sun. And it's also going to affect the magnetic field on the back side, or the night side, we call it. And here in a minute, you're going to see a very explosive event that happens called magnetic reconnection, where magnetic field lines will break and reform. And when that happens, we can get aurora. This is one of the main drivers. That night side reconnection is one of the main drivers of the northern lights and southern lights. So this is sort of that whole pathway from the sun and that big CME or solar wind transient that will come and impact Earth, affect the magnetic field, and then along the night side, we get that explosion happening, our magnetic field lines reforming, pulling particles in towards the Earth, dumping them into the polar atmosphere, and then watching as they become those beautiful northern lights that we all love to look at so much. So the reason that I love aurora so much, and I study it as part of my job, that's what I do most of the time, is think about aurora. But one of the reasons I love it so much is that it actually shows us electric currents that are happening in the sky above our heads, right? It's a visible signal of those electric currents. So it's something that's science based and it's connected to the physics, but it's also beautiful. It's a work of art, right? And that's why I think they're so fascinating for so many people. They really connect what's happening in space to our atmosphere, just a few dozen kilometers above our heads. And I think that's why people are drawn to them so much. I wanted to ask if anyone in this room had the privilege of seeing some of the aurora from the big G4 geomagnetic storm last Thursday. Was anyone out there? Excellent. How was it? Yeah, photos. Yep. So as you know, this was one of the biggest storms that we've had in the last 6 years. This was the biggest storm we've had in the last 6 years. It really caught us by surprise. We didn't have some of our data streams were down that are usually taking data and looking at the sun. So we actually didn't realize that a CME was didn't quite realize the CME was headed towards Earth. And we didn't really expect that to happen. We didn't, sometimes we're kind of waiting for it. And that was one of those just kind of last minute. You could see the activity building, but we didn't have that few days of advance notice that sometimes we do in other periods of time. I did want to show a couple of videos that I pulled from here in Calgary. This was, I think, northwest of Calgary, taken by Russ H. Brown. And that was, during one of those really bright periods during the G4 storm. And it just looks beautiful even on this bad projector screen up here. And then there's another one on the right taken from northern Minnesota. And this is an example of pulsating aurora, which I'll talk a little bit more about in a second. And that pulsating aurora can come in these patches that turns off and on. And it just looks gorgeous when you see it in real time. This was one of the nicer events that I've seen recently that someone has taken a video of. But you can see these sort of amorphous and strange looking patches that are just turning off and on and showing us that pulsating aurora and also that patchiness to the aurora. If you can believe it, aurora was seen in over half of the US states. So all the way down to places like New Mexico and North Carolina. Now it was a very, very faint glow on the horizon. So it didn't look like this down in those southern states, but people were able to get long exposures on their camera and see the glow of the aurora in places where they usually don't expect to see anything like that. So it was a really great opportunity also to connect with the whole country and talk about space weather and talk about the dynamics that happen in space to people that don't usually get exposed to that kind of thing. So let's dig into this pulsating aurora a little bit more before we move on. Pulsating aurora is caused in a little different way than the magnetic reconnection that I spoke about a few slides ago. And I wanted to bring this up because this comes back to our plasma waves. So we talked about that ocean of plasma that's out there in what looks like empty space. And we know that it's not empty, it's full of that sea of plasma, and we know that waves can occur in that sea of plasma as well. And when those waves occur, they can cause particles to get pushed along the magnetic field line. And if they get pushed in the right way, they're going to end up falling into the atmosphere, becoming aurora, and not coming back to space. So it's basically a way of pushing particles from space into Earth's atmosphere. And pulsating aurora is all about waves. So waves is what drives this pulsating aurora. I really like pulsating aurora because what you're actually looking at is plasma waves out in space. When you're looking at that turning off and on and that pulsing of the aurora, what you're looking at is waves in space that are turning off and on. Okay, so electric and magnetic field waves that are just pulsating at that same rate, and they're pushing those particles into the atmosphere. So it's really incredible to just think about what you're looking at when you see that pulsating aurora, if you ever have the chance to see it overhead. I did want to mention a sounding rocket mission that I had the privilege of being a part of, and we launched about a year ago in March 2022, not 23. So this was a year ago, and this was in Poker Flat, which is near Fairbanks, Alaska. And I'm going to play this video for you because this is pulsating aurora in real time. So it's a lot slower than that other video that we saw that was posted on Twitter that I grabbed. So it's this more of a gradual process, a gradual filling in of these patches and then a gradual unfilling of these patches. And it looks pretty nice in this video, which was taken by Aurora Chasers group up in Fairbanks. But the best part is when we shoot a rocket into this. So let me fast forward just a little bit to the point where we actually launch our rocket. Mm-hmm. So there's the first stage of the LAMP mission rocket that goes off, and you can see it goes right into that green pulsating aurora where you can see those patches hanging around everywhere. There's the second stage motor that lights up and brings it higher and farther as it traverses across the Alaskan countryside. And we're going to watch it just as the engines start to dim out, and it goes straight through these extreme patches of beautiful pulsating aurora, some of the best pulsating aurora that I've ever seen, and we were able to be there at the right time to launch a rocket into the middle of it and collect the data that we're all now very busy looking at and analyzing. So pulsating aurora, plasma waves, and shooting a rocket into that, even better. So the next thing we're going to kind of move towards is a little bit further away from Earth. So not in our atmosphere anymore. We're going to go a little bit further out, and we're going to talk about the Van Allen radiation belts. And these are regions of space plasma that are contained around Earth. And this is where charged particles get trapped within Earth's magnetic field. This also happens at other magnetized planets as well. And they can energize to incredible levels. Okay, so Earth's magnetosphere is a really, really great particle accelerator. It just takes particles and it can pump them up to really, really high energies. They can also get pushed along those magnetic field lines in the right way so that they fall into the atmosphere. And I know we've been talking a lot about space plasma, and some of you are like, well, I don't even really know what space plasma is. And it doesn't seem like it's all that relevant. So some of it does create aurora, which we can see with our eyes and we enjoy watching. But there's another consequence to this higher energy radiation that can come from the radiation belts and get dumped into the atmosphere. And that effect is relevant to our understanding of climate. So let me explain this to you for a second. This is the aurora essentially up here, but there's also other particles with higher energies that can penetrate further into the atmosphere than the aurora does. And those particles can create atmospheric constituents, such as nitric oxides and hydrogen oxides, that can circulate down to really low altitudes, so really down into the stratosphere of Earth. And the amazing thing about those particles is they're really good at eating ozone. So what we see in our studies is we see ozone depletions after we get strong injections or strong precipitation of these really high energy particles. So it's not just about aurora, and it's not just about space anymore. This is really about things that can contribute to our full understanding of our climate. Now, I want to stress that these ozone depletions are very localized. They're not going to spread over the whole Earth. But still, if we're trying to understand our climate models and we're trying to understand how ozone is created and destroyed and mixes throughout our atmosphere, we want to know when there's local depletions of it. And one of those causes is space precipitation. And if you ever can't really remember this idea of space precipitation, just think of energetic particles falling on your head, because that is in fact what's happening. So I want to move to the University of Iowa, where I'm from, a little bit more directly now, because there's a connection between the radiation belts we were just talking about and that institution. And in fact, that was where the discovery of the radiation belts originated. So this is Professor Van Allen here, also pictured here, holding up Explorer 1, which was the first US satellite that was launched into space in January 1958. And this satellite made the first observation of the radiation belts. And this was a great achievement. You know, first just getting something into space and having it work at all was a really great achievement. And then the ability to use that for scientific good and to use that for some scientific discovery was quite amazing. And again, I have the just really great, amazing pleasure of going to Van Allen Hall every day and working as my job. So still sometimes can't quite believe I'm there, but I am. And I've been able to sort of understand this legacy a lot more since I've been there. Another part of this story is Sputnik 2, which was launched by Russia in November 1957. So you'll notice it was before the US satellite, right? It was before Explorer 1. But they missed out on the discovery of the radiation belts. And the reason is because their data was transmitted through and captured by an Australian antenna. An Australian scientist wanted to work with the Russians to look at the data together and get some scientific discovery out of this. And Russia basically said, no, we don't want you to do that. We want the data for ourselves. We're not going to collaborate. And Australia said, okay, well, then you're not going to get the data. And so nobody looked at the data because Australia couldn't decode it and Russia couldn't get it. And then in January of 1958, so just a few months later, the US launched our satellite and we got our data and were able to make that discovery. So the Vernov belts never existed, and instead they became the Van Allen belts, but it was close. So always be open to working with others. There's an apocryphal story here when this discovery was made by some of the colleagues of Professor Van Allen. And the story goes that someone was looking at the data, the strip charts of the data laid out on the desk, and they had an insight, and they ran and they wrote a note and they taped it to Professor Van Allen's door, and it said, "Space is radioactive." I'm not really sure if that's true or not, because I've also heard that he was sitting at his desk and he just exclaimed, "Space is radioactive." But in one way or another, they got this data that really showed them that there were these high energy charged particles out there surrounding the Earth. And that's where that whole idea of radiation belts really came from, was back then. I'll also just point out as a very quick aside that this guy here holding up part of that satellite, Wernher von Braun, was a captured Nazi scientist, and he is the one that really jump-started all of the US entrance into the space landscape. So if you ever want to read more about that and that complicated history, it's really interesting. Okay, so let's move on to Jupiter, which does have space plasma surrounding it. It has a magnetic field. It has a magnetosphere. I'm going to thank Fran Bagnall for this nice figure here, which just shows the magnitude of Jupiter's magnetic field compared to Earth, but even compared to Saturn. It's just a giant. It's a giant of all giants out there in our solar system. Now, Jupiter has plasma, it has a magnetic field, it has a magnetosphere. Do you think Jupiter has radiation belts? Yes? It does. It does. It has plasma, it has magnetic field, of course. Yes, it has radiation belts. Do you think Jupiter has aurora? Heck yes, it does. I don't know if anyone has been paying attention to the JWST pictures that have been coming out, but one of the most fascinating ones I've seen has been this one of Jupiter with the aurora in both the northern and southern hemisphere. And it seems to just glow constantly, just glow consistently. There's people that are digging into this and trying to understand the aurora in more detail with some of our spacecraft missions. But I love this picture because it just is, the beauty of JWST and the detail that it can get from that space telescope. And it's showing that wonderful aurora. It stands up off the planet's surface. You can see it has a height to it. And it's just, these images are just gorgeous. So our heliophysics observatory is a whole host of spacecraft that we have in orbit, as well as a lot of observatory stations that we have on the surface of Earth. We're going to take a look at what some of this looks like as we zoom away from Earth and we look at some of the near-Earth spacecraft that we are using at the moment, and then zooming outside of Earth's magnetic field. So now we're outside of the magnetosphere and we're heading towards the sun. And we have a few more spacecraft that are out there in between Earth and the sun. And if we zoom out even further, we're going to eventually see that Earth kind of fades away into the distance and we head towards the sun itself. And we've got several missions that are orbiting the sun and observing that sun and that solar wind. And that's mostly what we have in our inner magnetosphere. And we're going to start to zoom out of that inner magnetosphere and get even further away to the outer planets and past the orbits of the outer planets. And we're going to eventually get so far away that we reach that boundary that we saw in the very beginning of this talk. Okay, the boundary of our heliosphere, what we call the heliopause. And here you'll see there's a couple of satellites hanging out past that boundary. And those are the Voyager spacecraft, and we'll be talking about them more in a second, that have actually exited our heliosphere. So gone beyond the boundary of the influence of our sun, and they're out there in interstellar space right now. So yeah, we'll talk about that Voyager mission. It has gone to the boundary of our heliosphere and then beyond, and the amazing stuff that it's been able to look at. I wanted to ask if anyone knows what this picture is. Have you seen it before? Yes, thank you. Pale blue dot. Yeah. Okay. I think a lot of you knew what this was. Maybe some younger people don't know. But this is one of those pictures that changed the entire world, right? When this picture came through. So this is the infamous pale blue dot. This is taken by one of those Voyager spacecraft when it was out past the orbit of Neptune. So it was really far out in interplanetary space. And Carl Sagan had this brilliant idea to turn the camera around, turn the spacecraft around, and point the camera back towards the solar system. And take this series of pictures that was meant to be a portrait of our solar system. So took a picture of each of our planets that we could see from Voyager at the time, including Earth. And there's a little bit of an artifact in the image, so it looks like this sunbeam that's just kind of like radiating right across Earth's orbit there. That's just the artifact of the image. But look at the smallness and the paleness and the distance to our world where all of us live and all of us will go through our entire lives. And then think about the vastness of space that mission has traversed to get to that spot and turn around and look at everything we've ever known. It's just incredible. I think he was brilliant for having that idea and knowing what that would mean to the public to turn around and take those pictures and have them available. JPL actually put up a whole mosaic in their building in California of the whole family portrait, and they had to keep replacing the picture of Earth because people would come up and touch it. They couldn't resist but physically touch that planet on the wall there, and just to get that connection of how far away it was when this picture was taken and what it means to them. So just some amazing stuff that Voyager did early on. So Iowa has had a long history of space exploration. We're part of the Voyager mission. I wanted to show some other photographs of different things that we've been involved in way back in sort of the beginning. of space exploration itself. So we have some images here of raccoons, which are basically rockets that are shot off of balloons into the atmosphere, satellites, so Explorer 4 and Pioneer 4, magnetometer calibration going on one of the lawns of the Iowa academic building there, and another testing setup for one of the satellites, used to be called Engine 4, now it's called Iowa 4. And there's just, some of that history that has gone on since the 50s at the University of Iowa. I'm going to show another few pictures here. There is the Voyager plasma wave subsystem. We'll talk more about that in a second. And testing of some various other spacecraft there, Cassini, which is a famous one. But I wanted to ask people in this room if they've noticed anything about these pictures. Dudes. Yeah, white dudes. Yeah, that's right. That's right. White dudes. These were great white dudes, right? They were, and they explored. They helped us to explore the entirety of our solar system and what we know today. But they were white dudes. So I wanted to take a brief intermission at this point in the talk and talk about something that's really important to me. And this is that the prevalence of gender, racial, and ethnic minorities in physics, which is including space physics and planetary physics, is disturbingly low. And other groups that are historically marginalized from STEM are also devastatingly sparse. Okay, so this includes all kinds of identities that are not the majority dominated. And the reason I want to talk about this is because I think that we need to have more public discourse. I think that all of you in this room and online can go talk to people about this when it comes up in conversation and have a really informed opinion about why this is important. There's a couple of things I want to bring up about this. One is this report that I was part of from the National Academies, where we looked at diversity, equity, and inclusion, which I think you call EDI here. Is that correct? Yeah. And accessibility in the leadership of competed space missions. And we looked at individuals who had led space instrumentation or space missions over the years through all the NASA divisions. And we came to the conclusion that it was remarkably homogeneous. And we were able to do a little bit of statistics by breaking out female leaders from non-female leaders. But any other category, we couldn't break it out. We couldn't do any other gender minority. We couldn't do any racial and ethnic minorities because those people were in the single digits. So we just couldn't even do statistics on the amount of people in those categories that have been leaders of anything related to space missions. So it was disturbing. It was eye-opening. We have an entire report on what different entities can do better to help this problem. But it was really stark to see those numbers come out of that study. I also want to mention the 2019 NSF report that said physics has the lowest share of women degree recipients within the broad field of physical sciences. And it's not for lack of interest, because space is awesome. And space interests every little kid that I've ever met in my life, right? So it's not for lack of interest. It is for a couple of different reasons, which I'll talk about in a second. Black geophysicists represent 2% of degrees awarded currently, which is just abysmal. So racial and ethnic minorities are not represented in our sciences at all. And the question is, kind of what do we do now? Like, what do we do with this information? I think that, in general, I can say things like, well, we need to change the landscape. We need to be more supportive. We need to encourage scientific inquiry at a younger age. We need to not use math as a barrier or a marker of who should be a scientist and who shouldn't. If you want to be a scientist, then you learn the math. Not if you're good at math, you become a scientist. Okay, so we do it the wrong way around, I think. We really need to be cognizant of what that says to our kids when we say it the other way. If you're good at math, then you can become a scientist, and I don't believe that. So for me, as a white woman in physics, I have some privilege for sure, but it's also been a really isolating place at times. And I take a lot of solace in finding community, finding supportive mentors. This is a recreation of the picture I showed earlier of holding up Explorer 1 in the National Academies building in DC. This is Robin Millen, one of my mentors. This is Sue Finley, one of the longest serving women at NASA. She was one of those original human computers that would do the math by hand when the space race was first starting. So I was really excited to meet Sue Finley there and have the opportunity to talk with her during this event. But what I do to try to help this kind of problem is I engage in activism. So that's a big part of what I do is I work with groups and try and just make the broader public aware of these issues. We try to create inclusive spaces and just really change the tone of what's going on in physics, space physics, planetary physics, and all sciences. So I'm going to leave it at that, and we're going to go back to our regularly scheduled program. But I just had to mention that, and it was a good spot to mention that when I'm showing those pictures of what science used to look like. Thankfully, it's becoming different, but we still have a lot of work to do. So the Voyager mission is a really incredible mission. We've already seen that pale blue dot picture. We've talked about it. A couple of other things that are really important to know about Voyager. It's a twin spacecraft mission. It was launched in 1977. Okay, it's that old at this point, and it's still going. We had some close flybys of Jupiter, Saturn, and several of their moons. Then they continued their journey out until they reached the outer boundary of that heliosphere, like we've seen before. Voyager 2 visited Uranus and Neptune and is the only spacecraft still to date that has ever visited those planets. Those planets are far away. It's expensive to get there, I understand, but there's some incredible physics going on there. They are magnetized planets. There's some really interesting stuff, and we have not been back since Voyager went by. And they are now so far away, these spacecraft, that it takes nearly a full day for the radio transmission moving at the speed of light to come back to Earth and get collected by our satellite dishes to be read in as data and interpreted. The data is also pretty sparse and getting worse, getting more and more degraded as time goes on, just because of that distance and the complications with reading radio waves from that far away. But I still think that's incredible that we're waiting a day for that data to come back to us from those little Voyager spacecraft. At Iowa, we had built the Voyager plasma wave subsystem. It looks kind of like a golden briefcase to me, but it's actually just an electronics board, which is attached to these really long antennas that are out there into our space plasma ocean. And those antennas are sitting there and recording those waves that are happening in our space plasma. So it's like putting little probes into the ocean and watching for wiggles, watching for waves. So we have this instrument on both of the Voyagers, and we're able to see those plasma waves as they come by. This was led by Professor Don Gurnett and co-investigator Bill Kurth. So let's take a look at some of those waves. And the way that we want to take a look at them is I don't want to just show you plots because plots are kind of boring. So what we're going to do is we're going to turn them into sound. This is a great project that a lot of people at Iowa have had a hand in, is taking our wave data, which if you just show this plot, people are like, I don't care. This just looks like a bunch of blobs. But you can take the plasma wave data and then artificially turn it into sound and sonify that data. And it becomes a lot more interesting. Okay, so we're going to take these plasma wave data and we're going to turn them into sound. So the first one I want to show is back to the Van Allen belts. So we're not all the way out of Voyager, we're back in the radiation belts of Earth. And these are Whistler waves. You're going to understand why when I play it in a second. And you can already see that there's a characteristic pattern to these waves shown by the sweeps through frequency. So if you sort of imagine in your mind what that's going to sound like, you can kind of see if you're right or not. But think about high frequencies sweeping down to lower frequencies in this characteristic pattern. So let's play and listen to what this sounds like from space. All right, so kind of like laser beams or aliens or something like that. You can hear that characteristic falling frequency, right, as it goes through that pattern that we see on the plot. These are called whistlers because they were originally heard from military forces out in the field during World War I that had these loop antennas. They were trying to listen for communication from the opposing forces, and they actually heard occasionally these little things like this, these whistler waves that would come up in that antenna when they had their headphones on. So it turns out that lightning in Earth's atmosphere can generate whistlers. They can generate plasma waves that are in the whistler range in Earth's upper atmosphere. These are a different type of whistlers that are created in the radiation belts, but they're the same kind of plasma wave and they sound the same. So people actually heard these way on the ground before we had anything, up in space listening. One of the reasons that we think that lightning exists on Jupiter is because we have observed whistlers at Jupiter. So let's hear what those sound like.
Jovian whistlers.
Okay, so if you think we have evidence of these same types of whistler mode waves that are being created at low altitudes by lightning on Jupiter itself, which is really incredible. And then finally, we're going to listen to sounds from Voyager itself. And this is when Voyager was out in interstellar space. So again, we've left the boundary of our heliosphere. We're out beyond the influence of the sun. It's probably very dark and lonely out there, but there's still stuff going on. So these are a couple of different events where interstellar shock waves passed over Voyager as it's flying on its orbit. And we get these sudden increases in oscillations in the electromagnetic field that are our plasma waves. And we can hear what that sounds like. So just to orient everything, this is the heliopause right here on this dashed line. So Voyager has left the heliosphere and everything to the right is out in interstellar space. And let's hear what these sound like. Here comes the big one. Okay, kind of eerie, kind of like a UFO sound almost. But this, I think, instantly makes this more interesting than looking at this plot alone. The fact that you can hear it and understand the changes in frequency and just how incredible it is that Voyager, way out in interstellar space, is observing these plasma waves for us. So that's everything I want to talk about tonight. I wanted to end with the idea that our solar system, whether it's in the sky above our head or to the farthest reaches, is a place of exploration and wonder. This is a quote from an art exhibit I saw in Finland last year. And it's a quote from Charles Bukowski. It says, "I sit here on the perfect end of a star, watching light pour itself towards me." And I just love that sentiment. And I hope you all have enjoyed this evening. And please be in touch and look up more if you're interested. Thank you so much.
Okay, so thank you on behalf of everybody. Thank you, Allison. And are there any questions from our local audience? So can you come down?
I can't get out, but I'll shout.
Okay, yeah.
What conditions cause a strobing aurora? Like strobing at maybe twice a second or maybe every 2 or 3 seconds? What conditions cause that effect?
I'll repeat the question for the online viewers. So the question is, what conditions cause strobing aurora, 2 or 3 beats per second sort of thing?
Yeah, so that's a really good question. We've known for decades that there's this sort of sub-second modulation, and usually it's embedded within the larger slow patches that I was showing earlier. So you'll see those large slow patches turn on and off, but then inside of those, you have a little bit higher frequency flickering like you're talking about. And those are, when we go back to thinking of our plasma waves, those are little substructure within our plasma wave bunches. So we have a a bunch of waves that comes by, and there's little structure inside there, and that's what's causing that sort of little flickering on and off. So it still all comes back to plasma waves, and it's just about the detailed fine structure that exists in those waves out in the magnetosphere.
Okay, yes.
Yeah, I was just wondering, the reconnection of the magnetic lines on the other side of the Earth. What kind of energies are associated with that when they connect?
Yeah, that's a really good question. We have an entire spacecraft mission dedicated to understanding the magnetic reconnection that's in operation right now. Magnetosphere multi-scale mission by NASA. We're not really sure what's exactly how to quantify the entirety of that energy release. Right now, we're able to look at particle heating, and we're able to make some inferences about what that energy release is. But yeah, that's one of the big open questions: how much energy is stored in the magnetic field, and how much is released during magnetic reconnection. So stay tuned.
So this is a comment from Gene Malone, who's a member, a retired member from our physics department, who said, for information, one of the founders of the University of Calgary's astrophysics program was Doraiswamy Venkatesan, who also spent time with Van Allen in the late 60s.
Yeah, and we were just talking about that earlier today, that it would have been amazing to really spend time with these people that were the first ones to put things into space and to take measurements in space. And you know, time has moved on, and we're now at a different place in our evolution of space exploration. But it's amazing to see what was done back then.
I have two questions. I think the first one is easy. Are there non-magnetic planets?
Are there non-magnetic planets? Yes. So there are planets that don't have an intrinsically generated magnetic field. Some of them used to, and so they still have some leftover small magnetic fields, like Mars, that are kind of entrained in the surface of the planet, and they create little tiny pockets of magnetic field, but nothing like the big planet encompassing magnetic fields that you see at Earth or Jupiter.
Right. And then the second question, I think, might be trickier. Why is there an 11-year cycle with the sun?
Yeah, that's also a very good question. People are definitely trying to study that and understand it. We see a large scale convection, at least over the time history that we've been observing our sun. We see sort of a large scale convection where sunspots move across the face of the sun in latitude, from higher latitudes and lower latitudes. And that follows that 11-year cycle, but we're not really sure what's happening in the layers underneath that cause that sort of large scale convection. But it seems to be, at least for now, a repeated cycle.
Okay, there's a question here, and then
Yeah, this is like almost related to the first question back there. Back around the Earth's poles have flipped from north to south a few times in history, and presumably that's going to happen again. And one of the reasons Mars has no atmosphere, I gather, is because it lost its magnetic field, and then the solar wind blew away the atmosphere. What kind of risks are we facing?
Yeah, so Mars is different in that it just didn't have a field reversal, but it actually its core slowed down and cooled, and it was unable to generate that dynamo that created a magnetic field any longer. So it's a different category than what we're seeing here at Earth, which is where we still have a nice active dynamo. We're generating our magnetic field pretty nicely. I'm sure that the field will reverse at some point in the future, because it has in the past. I don't think necessarily that we need to worry about it at this time, but you know, just like anything, it could happen. You know, there could be a monster explosion from the sun that we never saw coming, and that could happen as well. But from what we understand, it's a pretty repeatable thing. And I think with our human ingenuity, we can find a way to survive something like that.
But would that, for example, knock out all our radio transmissions and a bunch of transistors and a bunch of automated computer systems?
Quite possibly, if large solar wind transients hit Earth while the magnetic field was in transition.
There was a question back.
But one question was that one about like cell phones and electronic devices getting fried by torch stones.
Mhm.
Like there's a race for that. I want to ask you to comment on that risk as our societies rely more on those.
Yes, so the question was asking you to comment on the risk to our technology in space and the technology that we use every day on the ground. Of course, there's a risk. It's fairly well mitigated. We seem to understand how to bolster against that risk, at least as far as our power companies go and our satellite operations. But again, it's very unpredictable, right? Space is very unpredictable. We're not at the point yet where we can forecast it, even as well as terrestrial weather, and terrestrial weather still catches us off guard all the time, right? So we're in that same space where we're trying to be able to forecast ahead of time and see these disasters coming, but we're not at that point yet. And so there's always that risk that exists. Can't really be more specific than that.
So Ann Boehner said, thank you, very interesting and good job making the material accessible to the layperson.
Thank you.
And anonymous attendee said, what is the thickness of the heliopause? And does it protect Earth from interstellar high energy particles?
Yeah, okay, so that's a good question. I wouldn't say it protects Earth from high energy particles, but the sun's magnetic field, as it moves outward and creates that bubble, that heliosphere, can actually have a focusing or defocusing effect from high energy particles that are coming from, for example, galactic sources. So we can either have, those particles sort of focused in or defocused, and we see that. We actually can measure that from inside of our heliosphere. So we're not really protected per se, but we definitely see the effect of our sun's magnetic field on either pulling those really, really high galactic energetic particles towards the solar system or away from the solar system. But those are happening all the time. I mean, we're getting hit with them constantly. And that's sort of part of our background radiation that we live with in our solar system. And so it's not necessarily something that we have to worry about or have to be protected from.
Yes.
So I had a question about, I think it's Uranus that's like tilted on its side.
Yeah.
How does that affect, like, because Earth's geometry with its magnetic fields kind of not being poles towards sun, but how does something like Uranus impact like the aurora that might occur there?
Yes, that's why we need to go to Uranus. Can you just like make a phone call to NASA? Tell them that people are interested. Yeah, no, that's exactly right. We don't know. I mean, the Uranus system is incredibly complex because of that tilt. So it's like an Earth or a Jupiter, but laid 90 degrees on its side. And so you get an interesting effect with the solar wind hitting their magnetic field. And also there's a rotation of Uranus that comes with that 90-degree tilt of the magnetic field. And so you just have these constantly changing magnetic fields around it. It would be super, super interesting to understand. We think that there's going to be multiple places where aurora happens rather than just the two that we see, like, for example, Earth and Jupiter at the poles.
Okay, I see it. Yes.
I'm trying to understand the response better because I'm writing a paper on it for one of my astro classes. So I have a couple questions. What is the significance of the measurements that we made through the Voyager as the heliopause in interstellar medium research? Like, what does it tell us about interstellar medium?
Yeah, okay, so what does the measurements that we make from Voyager at the heliopause tell us about the interstellar medium? Yeah, okay, so there's a lot of interactions that happen between the interstellar medium and that magnetic field generated heliopause. And that's sort of the big thing in all of space physics is boundaries and gradients. So when you pass through that boundary, all of a sudden you're in a totally different plasma regime. And what happens there at that boundary is a whole lot of things. You have shock waves, you have reflected particles as a result of that shock wave, you have plasma waves that are kicked off and generated, and it's sort of like this whole zoo of plasma processes that happen right at boundaries. So we love to study boundaries. We love to study the boundary of Earth's magnetic field with the solar wind, and we love to study the boundary of the interstellar medium with the sun's magnetic field too. So look into all of that.
So in a recent paper that just got published, like March 6th or something, I was reading that and it said that the Voyager cannot detect low energy plasma, which is important to for us to be able to measure the location, the size of the heliosphere. Is that true at all?
So that's not quite true. I'm not familiar with the paper that you're necessarily talking about. I'm actually missing a Voyager science meeting to be here to talk to you all tonight. There's a meeting out in California these couple of days that I'm skipping to be here, which is fine.
Probably cold and snowy there.
In California. Yeah, but yeah, that's we can maybe talk afterwards if I know the exact paper that you're referencing, but there's so much of a rich data set. We are losing data though from Voyager, right? So we are losing some of that information that we had early on, and just because the spacecraft itself is degrading. I mean, it's been up there since '77. So it's amazing it still works at all.
There's a bunch of online questions here, but I actually wanted to ask one to kind of follow on that a little bit. We get one pass through the heliopause and that's it.
Yes.
And so is it variable enough or dynamic enough that it might overtake Voyager again?
I don't think so. No, we are well into the interstellar medium. We had 2 passes because we had 2 Voyagers. So
Yeah.
we were able to cut through the heliopause twice with 2 different spacecraft, but that's kind of all we get. There is a little bit of a boundary layer that we passed through, where we're not quite in the heliosphere, we're not quite in the interstellar medium, we're somewhere in between. And so we got a lot of information as we were traversing that boundary layer. But no, we're never gonna be able to turn around and come back through the heliopause.
And I noticed from the drawings that I've seen, I think Voyager went through the near end of the heliopause.
Yes.
Was that just luck?
No, that was intentional.
Okay.
Yeah. Although the primary mission of the Voyager was never to go out into interplanetary space. It was to go to these planets and to do these flybys of these planets. And then once we got all that amazing data out of that, the mission was extended and extended and extended. It's been obviously the longest extended mission now by far, because of all the amazing scientific results that it's led to.
Okay, thank you. And I'll say, can you comment on the impacts of plasma on the safety of human space travel, e.g. to Mars?
Yes. There's a problem with going to Mars because it was already pointed out to us that Mars has lost its magnetic field. Okay, and so Earth's magnetic field does a great job of taking energetic radiation and funneling it towards the poles. It takes that radiation and follows the magnetic field, and it might end up in our atmosphere, but it's at the poles where we don't live, we don't cross very often unless we're on a transpolar flight. So it's of little consequence to us as humans. When we go to Mars, we're just going to be buffeted by energetic particles whenever there's an event coming off the sun. There's no intrinsic magnetic protection there. So the only thing I think is feasible is that people on Mars would have to go underground. And if you're in those tunnels and you're under the rock, that's what your shield is for those energetic particles. But I can't see any way that humans are going to be walking. You see these pictures of humans walking around in spacesuits on the surface of Mars, and you really wouldn't be able to live in those little habitats up there.
Nobody survives the trip, right? Intended to make the trip.
We're not sure about that. Certainly, if there's nothing going on the sun, there's a better chance. There's a better chance of making it there.
Nobody survives the trip.
Yeah.
A question about the 11-year solar energy cycles. I assume they must affect our climate, and how does that cycle affect our climate?
Yeah, definitely. So that's like a whole realm I didn't even start to discuss, but the sun's output in terms of different wavelengths of light that are going to affect our climate, UV and other of those nearby wavelengths, that goes up and down with our solar cycle as well. And we see it on that 11-year cadence. We know that it exists. It's not a trend in one direction or the other, right? It goes up and down and up and down, but it certainly plays a role in our climate as well.
I'll go online again. What was the purpose of shooting a rocket into the aurora? Was it successful, and what was found?
Okay, so the point of shooting a rocket into the aurora is that we cannot fly a satellite through the aurora. So the aurora is too close to Earth, and we just can't keep an orbit going if we try and put a satellite through down low enough to go through the aurora. So the aurora is something like 100 kilometers above your head, and it's just not a feasible orbit to keep a satellite aloft. So we have to do things like shoot a one-shot rocket that goes up through the aurora for about 10 or 15 minutes and comes back down and crashes into Earth. And that's the data that we get. That's all we get. What was found was that that pulsating aurora was more energetic than we had thought before. And we wanted to understand the energy range that exists in that pulsating aurora. And we wanted to understand the plasma waves that were making it. So we took really detailed measurements from inside the aurora of the energies and of the magnetic and electric fields. And we're now trying to piece all that together to understand how those plasma waves I was talking about made that specific event last year.
Yes.
Yes, could we have enough data information from the Carrington event to kind of compare how many times stronger it was to the last week before storm?
Yeah, the Carrington event. So the Carrington event is the infamous solar storm where there was aurora seen as far south as South America. And, there were telegraph wires that caught on fire because there were so many currents induced at ground level because of that increased activity. We don't have a whole lot of information about that event. So everything that we've been able to do is just sort of estimating and approximating and piecing together what kind of activity would cause the amount of, like, for example, the auroras at such low latitudes. And so there's people that have been working on trying to approximate what that would be, but we really can't compare to what was seen last week. Last week was not anywhere close to the Carrington event, though, I'll say. So there's a wide range of difference between last week's G4 storm and a Carrington event.
Yes.
Did that take me to get a hold of me?
No.
I thought I would give you a acknowledgement. Anyway, you said something about women in your field.
Mhm.
And what about those black women that were on that show, the evaluation?
Hidden figures.
Yeah, they really existed, right?
Mhm.
Okay, I was wondering why you didn't have them on the thing, but the other thing too is, I've been studying the stars for a long time. And so my people. We have formations called, they're called medicine wheel, but that's a wrong name, that's a colonial name to it. So it identifies the Pleiades and sunrises, solstice, and all that natural movement. I think you talk about how minor or other than white boys being prevalent. It's just that they ignore the natural stuff that's already been invented, right? Like we understand what was going on in the stars before we had all these colonials.
Yeah.
And I think there has to be a breakthrough on that thought. Because there was a lot of answers, like for us, we talk about the star people.
Yeah.
All our ceremonies are designed and mirrored to the stars.
Absolutely.
So, and even Copper Canyon, you know Copper Canyon? It's in Arizona, they created this, they've had the whole constellation set up there in the mesa. And that was huge.
Yeah.
I've been studying, even in our QP designs, there's constellations on the teams.
Yeah.
I remember there's this one constellation, I'm not sure what it was, but the white guy said, you got one more star there, you shouldn't be there. And then you got the Hubble telescope.
And they found it.
There's one there.
Yeah.
So I mean, we knew that there was those stars before they had
Right.
this technology.
Yes, I appreciate your comments. Indigenous cultures have long studied aurora and the stars and the tracks that those stars take through the sky. And a lot about what we're just now discovering with modern science. There's a lot of distance that we can yet go to connect with those cultures and try to bring that understanding into our science. I'm part of a group called Aurorasaurus, where we are trying to work with those native populations and understand what they observe and how that can feed into what we're also observing with more modern techniques. And it's hard because there's a distrust. There's a distrust for a reason, but there's a distrust of, modern science and, sort of someone coming from the outside into a culture and saying, tell me what you know. But there is a lot of connections that can be made. So I really appreciate that comment. And I would hope that there's more of this work going on in our sciences now.
Well, there's been a renaissance of the old star knowledge coming forward. And I think the thing is that we say something and it's dismissed.
Mm,
And so we don't say anything.
right.
Oh, yeah, that's nothing, whatever it is, it's got that nice thing. But there needs to be a relationship between the
Exactly.
stars and us.
Yeah,
But they don't have that.
that's right.
We people say, oh, yeah, that's right, there's a relationship.
Yeah.
And we have to understand that we were made up of the same stuff that makes up the universe.
We are made of stardust. Yeah, that's right.
And that's what the next is.
Yeah,
Right?
absolutely. Yeah, thank you so much.